Okay. All right, we're going to talk today about Chapter 11, start Chapter 11 with limits. Um, so the informal definition of a limit is what is happening to f of x as x gets closer and closer to a number. So let's go back and think about back when we graphed rational functions. If we had something like f of x equals x cubed minus 8 over x minus 2, we know that the curve is not defined as x equals 2 because that would make the denominator 0. To help us graph, what we did is we can factor the numerator as x minus 2, x squared plus 2x plus 4 over x minus 2. And we see that the x minus 2's cancel, and therefore that confirms that there is a hole in the graph. What we can do is we can plot points for this part of the expression, the x squared plus 2x plus 4, but want to make sure that we deal with that hole. Remember that to find the whole value, we can ignore the values that we canceled out, and at x equals 2, we can take 2 squared plus 2 times 2 plus 4. That gives me 12. So that means that there's going to be a hole at 212. So if I take a look at this, our vertex ends up being -1, 3. And then we'd have a point at 0, 4, at 1, 7, and then we'd have a hole at 2, 12. We'll make that a different color. Okay. And then I can use the properties of symmetry to graph the other pieces. And that's what we'd have. And again, we would have this hole at that 212. All right. Let's also use the table feature of the graphing calculator to complete this chart. What we can do is into y equals, we can put the function at hand. We can put the x cubed minus 8 over x minus 2. But because I have these very specific values in the table, I'm going to enter those in. I'm going to go to second window to go to the table set. And instead of independent, for independent, instead of auto, I'm going to go to ask instead. That's really nice because that means that when you hit second graph to get to the table, you're able to enter in whatever values you want. So I can enter in the values here, 1.9, 1.99, etc. And then I can just fill those values of the table in. So I have 11.41, 11.94, 11.994. We have an error, 12.006, 12.06, and 12.61. Okay. As demonstrated when we did our graph with the hole and by the table, we can see that as x gets closer and closer to the left side of 2 or the right side of 2, this is important that it's from both the left and the right side of 2, the value of f of x becomes closer and closer to something, and that value here is 12. So with this function f of x, we say that the limit of f of x as x approaches 2 is 12. And here's how we're going to write that. We write LIM, and then below it, we say x approaches 2 by having a little arrow. And then because this was defined as f of x, we can put that there, and that equals 12. And so that's how we can write that. So this is the formal definition of a limit, that if f of x becomes arbitrarily close to a unique number L as x approaches c from either side, then the limit of f of x as x approaches c is L. And what we can see from our table, that as we go from either the left side or the right-hand side, both of these values and like both of these sets of y values, notice approach 12. The actual value is undefined, but notice that from the left and the right, if we go towards it, it approaches 12. And that's what a limit is. Okay. So even though the function did not exist at x equals 2, the limit of the function did exist as x approaches 2. So this is because f of x, again, this idea, f of x approached the same value as x approached 2 from either side. That's what means that a limit exists. It approaches the same value as x approaches a certain value from either side. So in this case, our limit was 12. Okay. So let's take a look at our next example. We're going to use a different expression here. We're going to use the graphing calculator to construct a table and use the result to estimate the limit numerically. And so this time we have the limit as x, the limit of x plus 1 over x squared minus x minus 2 as x approaches 1. So because x approaches 1, 1 is going to be in the middle of our table. And as far as setting up the table, these are values that you would like add and subtract from that 1. So adding this to 1 would be 1.001. We're adding 1 1,000th, adding 1 100th, adding 1 10th. Similarly, on the other side, we would be subtracting 1 1,000th, subtracting 1 100th, subtracting 1 10th. Okay, so that's kind of the thing. We put the value of the x value we're going towards in the middle and then go out that way. And then we can see what happens as we approach from either side. So I can change the function in here to x plus 1 over x squared minus x minus 2. And then in my table, I'll just change these values to 0.9, 0.99, etc. Okay, and then I'll just fill these values in. So here I ended up with negative 0.909, negative 0.99, negative 0.999, negative 1, negative 1.001, negative 1.01, and negative 1.111. Okay, we can see that we made our x values get closer and closer to 1. Notice that the y values are also getting closer and closer and closer to the same value, to negative 1. So the closer x gets to 1, the closer f of x gets to negative 1. So what that tells us is that the limit as x goes to 1 of x plus 1 over x squared minus x minus 2 equals negative 1. Now, notice in this case that f of 1 equals negative 1, and this is true. So there are times where the function is defined at that specific value, and the limit also has the same value. Okay. Look at another example, number 2. Here we have the limit as x goes to negative 1. And then we have the same expression that we're dealing with. So again, if we add 1 1,000th to negative 1, that would give us negative 0.999, negative 0.99, negative 0.9, and then subtracting it, we can obtain these values as well. Okay, so basically we're just trying to get closer and closer to negative 1 in this case. And so if I go, I can keep that expression the same, or the function the same. And so now I just want to change the values in my table. Okay, and we can fill these values in. So here I had negative 0.323, negative 0.332, negative 0.333. Here it was undefined. here, negative 0.333, negative 0.334, negative 0.345. Okay. So from the table, it does appear that we have a limit. Notice that as our x values are approaching -1, it looks like our y values are getting closer and closer and closer to -1/3. Okay. But notice the limit in number 2 can't be found using direct substitution. Even though f of -1 is undefined, the limit of f of x as x approaches -1 still exists. So here's a case that if we were looking for the limit as x goes to -1 of x plus 1 over x squared minus x minus 2 is -1, okay? But if we wanted to find f of -1, that, notice, is undefined, okay? So here we have a case where it's undefined, but the limit is still exists. So this really is our bottom line here. Sorry, my highlighter dropped. The bottom line is that the existence or non-existence of f of x when x equals c has no bearing on the existence of the limit of f of x as x approaches c. So that means that if f of c is undefined, there could be a limit, there might not be a limit, and we'll talk about that a little bit. Okay, so if it's undefined, you don't say that the limit doesn't exist. At this point, we would have to go through this process. So find the limit of the square root of x squared plus 9 minus 3 over x squared as x approaches 0. If we tried direct substitution, meaning if we tried to substitute 0 in, we can see we'd get something that's undefined. So that means that we'll have to create a table of values. So in the middle of my table is going to be 0. And then we're going to be adding 1,000th, 100th, and 1/10. And then I'll be subtracting 1,000th, subtracting 100th, subtracting, 1/10. I'm not good at drawing tables. Like, I always make them the wrong size. Sorry. Okay. And this is going to be x, and I will just call this f of x. Okay. And so we'd want to put this in the calculator as well. So now we can define this as the square root of x squared plus 9 minus 3 divided by x squared. And then we can use these values in the table, negative 0.1, negative 0.01, etc. Okay. And so if I fill these values in, I see that I have 0.1666, 0.1667, 0.1667, this is undefined, 0.1667, 0.1667, 0.1666. So we can see this is getting super close, right? But it's always seeming to approach this 0.1667, okay? 0.1667 is probably really going to be a fraction, right? Any idea what fraction 0.1667 is? That's really like 1/6, okay? And don't worry, we'll find values, better ways to than this table. But that's what we could say, that the limit as x approaches 0 of x squared plus 9 minus 3 over x squared then is going to be 1/6 according to our table. Okay. So will we always have a limit that exists? There are some limits that fail to exist, and they deal with some different types of discontinuities. One example is when f of x approaches a different number from the left side of c as the right side of c. So an example of that would be something like the limit as x goes to 0 of the absolute value of x over x. What that graph is going to look like is that anytime that x is positive, it's going to be 1. And anytime x is negative, it's going to be -1. The issue is that x equals 0, we can see that that's going to be undefined. So this is an example of a limit that doesn't exist. Notice from the left and the right, they're going towards two totally different values. This is an example of what's called a jump discontinuity. And essentially that means that it's different at each side. So as we approach 0 from the left, notice it was always -1. As we approached it from the right, it was always +1. It was different at each side. So again, the limit fails to exist. Okay. Okay. Another is if f of x increases or decreases without bound as x approaches c. So an example of this would be the limit as x approaches 0 of 1 over x squared. What would happen here is that we would end up with like -1, 1, -2, 1/4, -1/2, 4. So it would look like this, and basically approach this, would have these asymptotes, and do the same thing on this side as well. So that's what this looks like. Okay. And if we look at what happens as x is approaching 0, from the left and from the right, it is going to infinity. But so that's why this has a different name. We say that the limit doesn't exist because it's disjointed. So this is an example of an infinite discontinuity. And those are basically due to an asymptote. I know they're both going towards infinity, but they're never going to meet at infinity, right? Okay. So another type of discontinuity that there is the one that we had in our first example. The one that we had in our first example is an example of a removable discontinuity. And notice that these are okay. The limit can still exist when you have a removable discontinuity. When you have a removable discontinuity, that's like where when replacing the value, would fill the graph. Okay. So there is a discontinuity there, like we'd have to pick up our pencil to move from one point to another, but notice that like it will, notice that that would fill the graph up. Okay. So a removable discontinuity is fine. Jump discontinuity, again, it's not continuous. We have to jump from one to another. That's no good. Infinite discontinuity going towards an asymptote, that's no good. Okay. Another type of place where the limit doesn't exist is if f of x oscillates between two fixed values as x approaches c. If you were to think about putting these values in, what would happen, and hopefully you trust me, but if you were to substitute these values in to this, if it was the sign of 1 over x, that means that we're really doing the reciprocal of these, right? So if we took 1 over 2 over pi, that would really be like the sign of pi halves, which is 1. That's the sign of 3 pi halves, which is -1. 5 pi halves, which is 1, again, because we're doing the reciprocal. And notice that we're just going to keep oscillating here over and over and over again. So that means that what happens is that you see a graph, because it's oscillating like that, going back and forth between 1 and -1. That's a case where it does not exist. Okay, so this is where the limit does not exist, we'll say if there's oscillating behavior at that point. Okay. So I know all these are positive values, but the same thing as we know because of the unit circle would happen with the negative values. And if we were to graph this, I believe it ends up doing this, but the point is that at 0, it ends up oscillating, so we can't deal with it. Okay. So that's another time when the limit doesn't exist, if there's oscillating behavior. So that's not a discontinuity, it's continuous. It's just that oscillating behavior makes it a little iffy. Okay. I'll show you what it looks like. Okay, that's what it would look like if you tried to graph it. So see how it gets a little crazy in here? Okay, that's what happens. Okay, so when it's oscillating, that oscillating crazy behavior, that's another time that it doesn't exist. So here it says to use the graphing calculator to graph the function and then use the graph to determine if the limit exists. So we're just going to look at the graph and see what the graph tells us. So in example 4, we have f of x equals e to the x minus 1 over x. We can see if we're trying to go to the limit as x goes to 0, direct substitution, substituting it in won't work because that's going to be undefined. But I'm going to just zoom 6 it and see what we have here. And it looks fine, doesn't it? It looks totally fine. It looks like a very nice graph. So that must mean that there is a removable discontinuity at 0. The graphing calculator isn't going to show you where that removable discontinuity is. So what we can do here is we can just have a little sketch of this. And there just must be something, that hole at 0. We know that because of the, that it would be undefined there. And so this would be yes. And that's because there must be a removable discontinuity. And so if we look at it, then it looks like at 0, it's at 1. So we can see that the limit as x approaches 0 of this f of x is going to be 1. So because there was a removable discontinuity, then that was fine. And we could tell from the calculator that it looked like it was going to be approaching about 1. Number 5 is f of x equals sine of pi times x. So I'll just put that in, sine of pi times x. And if I graph this, we're looking at the limit as x goes to 1, and we can see here that this is what happened at x equals 1. And that's not oscillating behavior. Like, I know it's oscillating, but it's not like crazy, like one to the other, like within, all of these, within such a short period of time. So in this case, because of this, we can see that the limit does exist because it's continuous. And this is continuous, and we can see that the limit as x goes to 1 of this f of x is going to be 0 in this case. So here, because it was continuous, we were fine. Okay. Let's look at number 6. We have f of x equals the square root of x plus 5 minus 4 over x minus 2. We want the limit as x goes to 2. Oh, we want the limit as x goes to 2. We can see that that's going to be undefined. And we can see from our graph that it looks like that it looks like at x equals 2, that there's an asymptote that we see it approaches an asymptote over this way and this way. So because there's an asymptote at that, we're going to say no. And the reason is because there's that infinite discontinuity. Okay. So again, because of that infinite discontinuity, that's going to be a no. And then in number 7, we've got 4x minus x squared, all divided by 2 minus the square root of x. Oh, whoops, sorry. And if we were to graph this, we get something that looks like this. Okay. Remember, to be a limit, it has to approach it from both sides. And we can see that from the left side, there is no left side, but from the right side, there is. So what do you think we would say about this? Here we would say, no, it doesn't approach it from both sides. This, you guys, is called an endpoint discontinuity. And so the endpoint discontinuity means that there's going to be, like, it can't approach it from both sides because there's an endpoint that's there, okay? So that's an endpoint discontinuity, so that's going to be an issue. In our next example, it asks us to graph the function and use the graph to determine whether the limit exists. So this doesn't say to use a graphing calculator, so we're going to just try to do this by hand. So here, these are some piecewise functions. Here, we're looking at x squared plus 2x plus 1 when x is less than 1, and negative x over 2 when x is greater than or equal to 1. So let's see what we've got here. So if I graph x squared plus 2x plus 1 when x is less than 1, that means that, so this is going to have a vertex at negative 1, 0. And then there's going to be a point at 0, 1, and then there'd be a point at 1, 4. But since x cannot equal 1, there's going to be, like, that'll be an open circle. And then let me use my symmetry to graph the other pieces. So this would be that part of that graph. Now this is basically negative 1/2 x when x is greater than or equal to 1, so x could be 1. So we have 1, negative 1/2, and that's going to be a closed circle. And then essentially, this just has a slope of 1/2 going down this way. So this would be the graph of that piecewise function. And it wants to know if the limit exists as x approaches 1. We look at x equals 1 and notice from the left-hand side it's approaching 4. From the right-hand side it's approaching negative 1/2. That's a no. And we can see from the graph that that's going to be a jump discontinuity. Okay, because they're going towards different places. It's going to 4 and then it's jumping down to 1. So that would be a no because of the jump discontinuity. Now, what about this next one? The limit as x goes to 5 of f of x. And here it says that f of x equals 1 when x does not equal 5. But when x does equal 5, it's at 3. So x is always 1, or sorry, f of x is always 1 unless it's 5. But when x is 5, f of x is 3. So would a limit exist here? I know maybe instinctually we are saying no because we would have to jump to get to that, but let's think about it. Are we approaching the same y value from the left and the right? We are. As x approaches 5 from the left and from the right, it's going towards this removable discontinuity. So yes, this does have a limit. The limit as x goes to 5 of f of x equals 1, even though f of 5 equals 3, okay? And again, this is because this is a removable discontinuity, and a removable discontinuity is okay, okay? So yes, the limit does exist because of that removable discontinuity. And you might say, well, we're jumping here, but we're not. Again, this is approaching the same value from both sides. Here we were approaching different values. That's the jump. So here, because we're approaching 1 from both sides, that's the limit as x approaches 5. And so now we've seen cases where the limit as x approaches c is the same as f of c, and when it's different, and even when sometimes when f of c doesn't exist. So again, that we go back to this idea that the existence or non-existence of f of c has no bearing on the limit as x approaches c. Okay. So based on what we've talked about, let's use our understanding of limits that we've just looked at and the graph to try to answer each problem. Let's look at and see if we can find what our f of negative 2 is. F of negative 2 is at an asymptote, so that's undefined. What about the limit as x goes to negative 2 of this random function? We'll notice that it's approaching an asymptote, and so we would say that the limit does not exist. And if you wanted to justify that, I always like to justify everything. That's because that's an infinite discontinuity. Okay, so when we're going towards negative 2, it's going towards that asymptote, that infinite discontinuity. What about f of 0? The value of the function when x is 0, we see we have a closed circle at 4. So the value at f of 0 is equal to 4. So what about the limit as x approaches 0? Do you see that it doesn't approach 4 from both sides? This would be an example of a limit that does not exist. And if you wanted to justify it, you could see that there's a jump discontinuity there. Okay. What about f of 2? F of 2, we see has an open circle. There's no closed circle, so f of 2 is undefined. What about the limit as x approaches 2? From both the left and the right side, it's going towards that open circle. That open circle looks like it's at 1/2. So again, even though it's undefined, because it's approaching that same open circle from both sides, the limit does exist. And I'm going to say that that's about at 1/2. And remember that it's okay for a limit to exist even though the function doesn't exist when there is a removable discontinuity. So remember, removable discontinuities, limits can still exist. Okay. Letter G, f of 4. F of 4, it looks like has a value of 2 because there's a closed circle at 2. So when x is 4, the function is defined as 2. What about the limit as x approaches 4? What happens as we approach 4 from the left and the right? Well, doesn't it look like there's an asymptote here? I mean, obviously this is here, but in this case, notice that they're both approaching that positive infinity. So this is a case where the limit does not exist. And again, because it's going towards infinity, this is an example of another infinite discontinuity. Okay, so I think those are really, I love this graph because it just talks to us about the idea that it just drives that home, that it doesn't matter if f of c exists, the limit can still exist. And just because f of c exists doesn't mean that the limit exists. So those are independent of each other, okay? There are some limits that are not that hard to come by, that we can find by direct substitution. So an example are 1, 2, and 3. Let's find the limit as x approaches -3 of the cube root of 10 plus 3x. All we do in these cases, you guys, is to substitute the value in. So I'm going to take the cube root of 10 plus 3 times -3. I can tell that's going to be 10 minus 9. That's going to be the cube root of 1, which is 1. So I know that the limit as x goes to -3 of the cube root of 10 plus 3x is 1. Okay. We couldn't do direct substitution in those other problems because we were getting something undefined. But if it's not a problem, direct substitution is always a super nice way for us to find those problems. Let's do the same thing in number 2. The limit as x approaches 1/4 of the tangent of pi times x over 2. Well, putting 1/4 in isn't going to make it undefined. So let's find the tangent of pi times 1/4 or pi fourths all over 2. So what is the tangent of pi fourths? The tangent of pi fourths is 1. So we have 1/2. So the limit of the tangent of pi x over 2 as x approaches 1/4 would give us 1/2. Aren't these nice? I like these. What about the limit as x approaches 1 if we're doing the arc cosine of x over 2? So that means that we're going to put in 1 in for x, and now we want to find the arc cosine of 1/2. Is that possible? It is. Arc cosine of 1/2 is pi over 3. So we can say the limit of arc cosine of x over 2 as x approaches 1 is going to be pi over 3. Aren't those nice? So we can use direct substitution as long as we don't have something undefined when we do that. The next example says to graph the function and then to use the graph to determine whether the limit exists. So again, we have f of x equals the square root of x minus 4 if x is greater than 4, and that it's at 8 minus 2x is if x is less than 4. And it wants us to decide what the limit as x approaches 4 is. So we can see that there is no value when x is 4. So let's use this idea of limits to help us out a little bit. So let me graph the square root of x minus 4 when x is greater than 4. So I'll start at 4 and then make an open circle. 4 minus 4 is 0, so there's going to be an open circle at 0. And then 5 minus 4 is 1. And then we would take 8 minus 4 is 4, square root is 2. So this is what this would look like. And if you know your families of functions, that makes sense that you'd have like an endpoint at 4, 0 in that shape. And then 8 minus 2x if x is less than 4. Well, the y-intercept is 8. My slope is -2. And then instead of plotting a point at 4, 0, because it only is true when x is less than 4, I'll leave that as an open circle, and then I can fill in the rest of this graph. And what I found when I graphed both pieces of that piecewise function is that it approached the same value, didn't it? From the left and the right, the function approached 0. Okay, and we can see that this was just a removable discontinuity. So again, if you have a removable discontinuity, then those are okay. Okay. So now we're going to do some properties with limits. Again, these are pretty intuitive. If you have the limit as x goes to c of b, like a constant, that's just going to be that constant. If you have the limit as x goes to c of x, that's just going to be the value c. So there are these basic limit properties, or just some basic limits. And then these are the properties of limits that we're going to take a look at. And kind of use, we use the properties of limits if we know certain limits and we want to do some operations on them. So here we're saying that the limit of f of x as x goes to c is L, and the limit of g of x as x goes to c is k. So notice it's when we're approaching the same value. We have that same c value. So if we have a scalar multiple, so that means if we're multiplying the function by something in particular, if we take the limit as x goes to c of that scalar multiple, we can pull the scalar multiple out. If we have the sum or difference of two different functions, we can then use take the sum or difference of the actual limits instead of adding the functions or subtracting the functions together and then taking the limit. The same is true with the product and the quotient and a power. So those are nice properties of limits. So instead of doing the operations on the functions themselves, we can kind of use the individual limits to help us out with that as well. And we'll practice that a little bit in these next examples. This tells us that the limit of f of x as x goes to 3 is 7, and the limit of g of x as x goes to 3 is 12. And it wants us to find the limit, these different limits. One thing that I want you to keep in mind that's best practice is to keep the limit notation in the problem until the substitution occurs. Okay, I know you know that the limit might be true, but really it needs to stay in the problem to be appropriate notation. Okay, so in number 5, they're asking us to find the limit of f of x plus g of x squared when x approaches 3. Well, we can use our properties and think about this as the limit as x goes to 3 of f of x plus the limit as x goes to 3 of g of x, and then we can square that based on all the properties. Okay. So this is me utilizing those properties of limits. Now it's legal for me to take the limit of f of x as x goes to 3, which is 7, and the limit of g of x as x goes to 3, which is 12, and for me to continue. Okay. So again, I had the sum and then the net product that I could use, and so now I'm just going to take 19 squared, which is 361, and I can evaluate that limit. In number 6, I have the limit of g of x to the 1/2 as x goes to 3. So what that means is I could find the limit as x goes to 3 of g of x, and then raise that to the 1/2 power. And so the limit as x goes to 3 of g of x is 12. And so really I'm going to have 12 to the 1/2, which I know is the square root of 12. And let's simplify that. That can be simplified to 2 root 3. In number 7, we have a multiplier. So what we can do is pull out that 2, but also because we have the quotient, we can separate that out. So we can take 2 times the limit as x goes to 3 of f of x, and then divide that by the limit as x goes to 3 of g of x. Again, just using those properties I happy clouded on the other page. And so now that means that I have 2 times 7 over 12, essentially. Just taking that. So the limit of f of x as x goes to 3 was 7. The limit of g of x as x approaches 3 is 12. And then I can just simplify. This gives me 14 over 12, which is 7/6. Okay. So we can use those properties of limits to help us out. So here we didn't know what f of x was or what g of x was, but we could use the properties of limits to find out what those different operations on the limits. Okay. All right, so finally, we're going to let f of x equal, here we're going to define f of x and g of x. We're going to let f of x equal x over 3 minus x and g of x equals sine of pi times x. And we're going to find these limits. Okay. And we'll have luck with these. We're not going to have to do the crazy calculator thing. So in number 8, what we can do is we can say that we have the limit as x goes to approaches 2 of f of x. Okay, sorry, I ran out of disk space. You know me. Hopefully you guys got all this. Did we get all this? Sorry. Okay, so we just use the properties of limits. All right, so next example, we're just going to be able to use direct substitution for these, okay? So we're going to have the limit of f of x as x goes to 2, so let's just substitute that in. So we've got 2 over 3 minus 2. We can evaluate that, 2 over 1, so that's 2. So what we find is that the limit as x approaches 2 of f of x equals 2. Great. Okay. Now in number 9, we have the limit as x goes to 2 of g of x. All right, well, let's just sub it in. So we're going to use direct substitution. So we're going to say the sine of pi times 2. So that's the sine of 2 pi, and that's just going to be 0. So by direct substitution, the limit as x goes to approaches 2 of g of x is 0. Well, now in number 10, we can find the limit as x goes to 2 of f of x times g of x. Well, do you really want to multiply these together? I don't. Since we know the two limits as x goes to 2, let's use the properties of limits here. And we know that if we have a product that we can take the limit of each function and multiply those together. So the limit as x goes to 2 of f of x we found was 2, and the limit as x approaches 2 of g of x is 0. And so what that means is that we would just take 2 times 0, and that would give me 0. How about the limit as x approaches 2 of g of x minus f of x? Well, again, because it's a difference, we can take the limit as x approaches 2 of g of x, and then subtract from it the limit as x approaches 2 of f of x. Well, I know that from number 9 that this gives me 0, and from number 8 that this gives me 2, and so then I can subtract, and so that would give me negative 2. So those properties can be pretty handy, so that way you don't have to worry about, recreating other functions. All right. So that is a little bit of an introduction of limits, and we will learn more as we progress through the chapter. And again, just be a stickler on the notation on your assignment. I know you're smart, but don't do too many steps in one. Okay. All right. Have a great day.